Good morning.
Anybody got any questions about anything before we get started?
Nope, I don't think so. Or at least I don't.
Well, we're starting with rational functions today on page 160. As a reminder, I am recording all of these lectures and posting them on D2L for our class. They are unlisted on YouTube, so people can't find them by just searching. Okay. So a rational function is a function of the form f of x equals n of x over d of x, where d of x is not equal to 0. The numerator and denominator are both polynomial functions, and the domain of a rational function is a set of all real numbers such that our denominator is not equal to 0. So let's start by simply finding the domain of this rational function. We'll write it in interval notation. We've been doing this for a long time, so it's nothing new. We know our domain's all real numbers unless we have a variable in the denominator of a fraction or under an even index radical, and we have the situation where we have a variable in the denominator. So we're going to set that denominator equal to 0, solve, and exclude. It factors nicely into x minus 4 and x plus 1. We get that x cannot be equal to 4 or negative 1. I always like to draw a number line to help me with my interval notation here. We don't want negative 1 or 4, but we want everything else. Aaron, you want to mute? Thank you. So what will our domain be in interval notation?
Negative infinity to negative 1, union negative 1 to 4, union 4 to infinity.
Perfect.
Non-inclusive.
All right, so now we're just going to do more than just find the domain of these functions. We are ultimately going to graph them. But before we get to that, I want to look at our more basic, our parent rational function f of x equals 1 over x. We know that this function is undefined when x equals 0, because that's the value of x that makes the denominator equal to 0. Well, when a graph is undefined at a particular x value, we're frequently still interested in what's happening near that undefined x value, what's happening on the left and the right side. When we get to calculus, we're going to talk about this a lot, and we're going to call it the limit, but I'm not going to get into that calculus notation in here. So we should ask the question, how does f of x behave as x approaches 0? So I'm not going to use the calculus notation using the limit, but I am going to write it this way, as x approaches. So this arrow in math frequently means approaches. So as x approaches 0, but I want to say the left side of 0. So we put a little negative. It looks like an exponent. It's not an exponent, but that indicates the negative side of 0, which would be the left side of 0. So as x approaches 0 from the left, f of x, which is simply our y value, we want to figure out what number the y value approaches. So if we just follow our graph as x approaches 0 from the right, what's happening to the y value? what number is it getting close to?
Negative infinity.
Negative infinity. And then we also want to look at our graph as x approaches 0 from the right side. So we use the little plus for that notation to indicate from the positive side. We want to know what our y value is getting close to. So again, we'll just follow the picture. As x approaches 0 from the right, what's happening to that y value? This time it's approaching positive infinity. So it's getting bigger and bigger and bigger and bigger. Okay, questions on that so far? All right, well, let's also look at what happens as the x value approaches negative infinity. What happens to the y value?
It gets closer.
Hold
to
on,
0.
Anthony. Hold on. I want to highlight my picture. Hold on. So as x approaches negative infinity, we're looking at what's happening to the y value. Now I'm ready, Anthony. Go ahead.
It gets closer to 0.
It gets closer to 0. Is it going to ever cross the x-axis, like, and go up into the positives?
No,
Why not?
because what do I say?
Because
Because the x value is in the denominator, and there's a positive one that's dividing it.
So he's on the right track there. As x approaches negative infinity, all those x values are negative numbers. So if you take those negative numbers and plug it into our function, we have a positive 1 in the numerator divided by a number that's always negative, while a positive divided by a negative is always negative. So as we go to the left, we're just getting closer and closer and closer to 0. It's never going to hit 0. It's never going to cross over into the positives because we're taking positive 1 and dividing it by a negative number. So this approaches 0, but I want to say from the bottom side. Well, the bottom side is, once again, the negative side. And then lastly, we want to look at what's happening to the y value as x approaches positive infinity. So again, we're going to follow our graph. If my pen wants to work for me. As x approaches positive infinity, what's happening to the y value?
The y value also approaches 0.
The y value again is approaching 0. And just like as we were going towards negative infinity, this is never going to cross our x-axis and dip down into the negative numbers because x is approaching positive infinity. So we're only plugging positive numbers in, and a positive 1 divided by a positive number is going to remain positive. So this just gets closer and closer to 0, never touches 0, never crosses over into the negatives. I said positive, into the negatives. So it's approaching 0 from the positive side. Well, this graph here has 2 different lines that our graph gets really, 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 really close to, but never ever touches. It's happening on the y-axis, and it's also happening on the x-axis. A line that a function approaches, gets really, really close to, but doesn't actually touch is called an asymptote. In this section, before we get to graphing, we are going to study 3 types of asymptotes. They're all lines: vertical, horizontal, and oblique, which just means like a diagonal line. Y equals 2x plus 3, something like that. because rational functions almost always have one of these types of asymptotes. So let's start with a vertical asymptote. The line x equals a is a vertical asymptote for the graph of a function if f of x approaches either infinity or negative infinity as x approaches some number a from either side. Well, we saw that up here. So that's the first thing we did here in the blue. X approached a particular number. See, in our definition there, it said it approaches a, some number a. So we're approaching x equals 0 from either side, and we got positive and negative infinity. So that tells us that we have a vertical asymptote. Vertical asymptotes can look a variety of different ways. So I have the asymptote dotted in the red. That's the vertical asymptote. Frequently, we used a dashed line for asymptotes because they're not actually part of the graph. They're like guidelines for us to draw in the graph. So we have this vertical asymptote, and our graph could be pointing towards negative infinity on either the right or the left side, or it could be pointing down towards negative infinity on either the left or the right side. Please note that a rational function can have none, one, or several vertical asymptotes. Vertical asymptotes are definitely the most common types of asymptotes. The graph of a function can never ever cross a vertical asymptote. The other two we'll learn can be crossed, but a vertical asymptote can never ever be crossed. Something else that occurs with rational functions is a hole in the graph. And when I mean a hole, I mean your graph was going along and then all of a sudden there was a hole and then it kept going as it was. A hole doesn't change the direction of the graph, where like an asymptote does. It guides it and it has to get closer and closer to the asymptote without ever touching it. Well, if a rational function has a common factor in its numerator and denominator, then a hole exists in the graph of the function at the 0 of that common factor. And once we do an example, I know I'm doing a lot of talking here. Once we do an example, it's going to start tying things together. So let's talk about how we go about locating vertical asymptotes in holes. You're actually going to be looking for holes first. Holes occur when we have a common factor in the numerator and the denominator. So we're going to start off by factoring the numerator and the denominator of our rational function. Then we're going to look to see if there is a common factor. If there is a common factor, you're going to cancel that common factor, simplifying the rational function, and then you're going to write down that a hole exists at whatever the 0 of that factor is. If there is not a common factor, you're just going to proceed to the third step, which is where we identify our vertical asymptotes. The vertical asymptotes exist at the 0s of the simplified denominator. So if there was a common factor and you canceled it out, simplifying the function, to find the vertical asymptote, you would then set that simplified denominator equal to 0 to get your 0. If it didn't simplify, well, then you just use the denominator of your original problem. So let's locate any holes or vertical asymptotes. We're going to start by factoring our function. The numerator doesn't factor. The denominator, that should factor. 2x plus 5 and x minus 3 work. So we look to see, do we have a common factor? And we don't. We don't have the same thing on the numerator and the denominator, so that means there's no hole. And it was because we had no common factors. Now we move on to the vertical asymptotes. Vertical asymptotes are located at the zeros of our simplified denominator. This didn't simplify, so we're just looking at the original one. What are the zeros from our denominator?
One would be +3.
One would be +3.
And yeah, man.
-5/2.
-5/2. And that's it. Now, I want to comment about notation. Asymptotes are lines. So we are writing equations of lines. If you have multiple vertical asymptotes like we did here, you cannot, I will not accept x equals 3 comma -5/2. All right, we are writing equations of lines. Vertical lines are always written x equals a number. You got to write that x equals every single time. Questions on that example?
I have difficulty writing the ampersand.
Oh, well, then
Would
write
a
the word
comma
A.
also
Then
work?
write out A. I don't care about an ampersand. I'm just don't feel like writing out the word and.
Okay.
Anybody else? Questions? But I love, Anthony, that you know that that's called an ampersand because not many people do. All right, let's try another one. We're going to start it out the same way. We're going to start by factoring both the numerator and the denominator, seeing if there's a common factor. Got a GCF of x on top. I did. Bottom factors into x -3 times x -4. So we look and see that this time we do have a common factor, which means that we can simplify our rational functions, right? Because these cancel out. And g of x is equal to just x over x -3. There was a common factor, therefore there's going to be a hole. And that hole is at the zero of that common factor. So we're going to have a hole at x equals 4. And again, got to put the x equals in there. We have a hole at x equals 4. How many vertical asymptotes are we going to have?
One.
Just one, because we're going to be using this simplified version for our asymptote. What is that one vertical asymptote going to be? Oh, we set that simplified denominator equal to 0 and solve. We're going to have a hole at x equals 4 and a vertical asymptote at x equals 3. Questions, anybody? And what I'm writing now, you don't have to write like I guess you're not really writing a test for me now. But even for the take-home quiz, I'm trying to be thorough in my explanation. So when you guys review your notes, you remember, oh yeah, there was a hole because we had a common factor, x -4. Nobody? Questions? I do think it's a little easier once we actually do an example because all those words sounded complicated. Factoring's the hardest part of it all. Next up are horizontal asymptotes. the line y equals b, so see it's y equals a number this time because that's how horizontal lines are. The line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x approaches positive or negative infinity. All right, well, as we're going to positive and negative infinity, our y value approaches a specific number. We saw that happen in our second two kind of questions here. Okay. X approached positive and negative infinity, and the y values approached a specific number on either side. Right? It approached 0, so that is the definition of a horizontal asymptote. I always think of a horizontal asymptote as where the graph's like leveling off. Right? It doesn't go totally horizontal, but you know, it's where the curve gets flattened. Oh, we could have a horizontal asymptote. Only one of the ends of the graph has to tend towards the horizontal asymptote. So it could come in and we're getting closer and closer as x approaches positive infinity. It could be from the top, the bottom, or you'll notice that third picture shows that a horizontal asymptote can be crossed. It can, but the graph has to come back to it. It can't just cross it and ignore it. One of the ends has to tend back. And then we have the similar pictures as x is approaching negative infinity. Some notes here. Horizontal asymptotes imply that a function approaches a constant value as x gets large in either the positive or negative direction. So that's the whole leveling off. We're getting closer and closer to a specific number. And as I mentioned, the graph of a function can cross a horizontal asymptote, just not at the ends. So let's talk about how we locate horizontal asymptotes. Totally different from vertical asymptotes. Here, we're going to be comparing the degree of the numerator with the degree of the denominator. That's going to tell us about the horizontal asymptote. So if we let f of x be a rational function with no common factors, yeah. So this means that we should be using the simplified version if our rational function simplifies for horizontal asymptotes as well. If the degree of the numerator is less than the degree of the denominator, then a horizontal asymptote exists at y equals 0. So that means that we would have something like g of x equals x squared over x to the third plus 1, something like that. All right, you know what? I'm actually going to change this to an easier example because I want to show you something. I don't want you guys to just, memorize these things. I think it's easier to remember them if we understand them. So I'm going to try to explain why this ends up being what we get for a horizontal asymptote when the degree of the numerator is less. So I'm just going to make up an XY chart. We have our x value and then our function x over x squared plus 1. So I'm just going to start plugging in some x values. Okay, so plugging in 1, I'm going to get 1 over 2, so I get a half. If I plug in 10, I'm going to get 10 over 101. If I plug in 100, I'm going to get 100 over 10,001. If I plug in 1,000, I'm going to get 1,000 over 1,000,001. What's happening to the overall value of this fraction as x gets larger? you know, and maybe you need to get a couple decimal approximations to really see the pattern.
The fraction's getting smaller.
The fraction is getting smaller, smaller and smaller and smaller, that eventually it's going to be practically zero. So that gives us a horizontal asymptote at y equals 0 anytime the degree of the numerator is less. If the degree of the numerator is less, that means the degree of the denominator is more, and the denominator is what we're dividing by. So if we're dividing by a number that is like increasingly larger and larger compared to the numerator, of course the value is going to get smaller because we're dividing by this big number. So that's what happens when the degree of the numerator is less than the degree of the denominator. Horizontal asymptote at y equals 0. Our next situation is when the degree of the numerator is equal to the degree of the denominator. So maybe something like f of x equals x squared over x squared plus 1. Then we have a horizontal asymptote at y equals the ratio of the leading coefficients. You know what, here, I'm going to throw a coefficient on this one. Let's make that 3x squared over x squared plus 1. So I'm going to do the same thing. I'm going to make a little XY chart and show you why we get what we get. Plugging in 1, we're going to get 3 over 2. Plugging in 10, we get 300 over 101. Plugging in 100, that's 30,000 over 10,001. And plugging in 1,000, that gives us 3 million over 1,000,001. Well, when we have the number like 1,000,000, you know, 1 doesn't really matter so much, even with these 10,000. So if we kind of look at what's happening to the value of this fraction, if we kind of ignored that plus 1, because as we're tending towards infinity, plus 1 isn't going to make a real difference. Notice all these zeros cancel out, and what we're left with over and over again is 3 over 1, which is the ratio of our leading coefficients. So when the degrees are the same, the values are growing at approximately the same rate. The only thing that makes a big difference is the multiplier out in front. Any questions on that? All right, well then our last case is when the degree of the numerator is greater than the degree of the denominator. So maybe we have something like x squared plus 1 over x. When the degree of the numerator is larger, there is no horizontal asymptote. And we can see that from a little XY chart again. It's actually just going to be the flip of the red, since I just flipped the fractions there. So when I plug in 1, I'm going to get 2. When I plug in 10, I'm going to get 101 over 10. When I plug in 100, I get 10,001 over 100. And when I plug in 1,000, I'm going to get 1,000,001 over 1,000. So we can see that the y value is not leveling off at some particular number. It just keeps growing bigger and bigger and bigger. Since the degree of the numerator is larger and the denominator is smaller, that means that what we're dividing by is a number that is substantially smaller than the number in the numerator, and it's just going to keep growing if we're only dividing by kind of a small number in comparison. So that's the reasoning behind our three rules, but we need to remember if the degree of the numerator is less, horizontal asymptote at y equals 0. If the degrees are the same, y equals the ratio of the leading coefficients. If the degree of the numerator is more, no horizontal asymptote. Right, so let's locate any horizontal asymptotes. All about comparing the degree of the numerator with the degree of the denominator. In this case, the degree of the numerator is less than the degree of the denominator. Are we going to have a horizontal asymptote?
Yes, at
Yes.
y equals 0.
Right? The degree of the numerator is less, so that means we're taking a small number, dividing it by a big number. The overall value of the fraction is going to get smaller and smaller and smaller until it's practically 0. So we get a horizontal asymptote at y equals 0. In our next example, the degree of the numerator is equal to the degree of the denominator. So the value of x is growing at approximately the same rate. The only thing that makes a big difference is our multiplier out in front. We're going to have a horizontal asymptote at y equals the ratio of our leading coefficients, 5/1, but of course we want to write that just y equals 5. And you got to have the y there. This is the equation of a horizontal line. We got to put the y equals there. Any questions so far? In our last example here, the degree of the numerator is greater than the degree of the denominator. So we've got this big numerator and we're dividing it by this smaller number in the denominator. When we're dividing by a number smaller than ourselves, it's just the number just keeps getting bigger. So in this case, we have no horizontal asymptote. Questions on horizontal asymptotes? All right, let's move on to our oblique asymptotes. So these are diagonal lines, like y equals 2x plus 3. So this is going to be a line of the form y equals mx plus b. So the line y equals mx plus b is an oblique asymptote or a slant asymptote of the graph of a function if our y value, f of x, approaches mx plus b, that's just some number, as x approaches infinity or negative infinity. Please note that an oblique asymptote only occurs when the degree of the numerator is exactly 1 larger than the degree of the denominator. It has to be exactly 1 more. And like a horizontal asymptote, the graph of a function may cross an oblique asymptote, just not at the ends. So notice that when we talked about horizontal asymptotes, we said if the degree of the numerator was larger, there was no horizontal asymptote, but an oblique asymptote only occurs when the degree of the numerator is larger than the denominator. So that means that a horizontal asymptote and an oblique asymptote cannot occur at the same time. So how do we go about finding our oblique asymptote? We're actually going to divide. Since the degree of the numerator is 1 larger, we can perform division, like this one right here. Right? We could do long division there and divide the numerator by the denominator. Since the dividend and the divisor only differ by 1, the degree of the numerator is only 1 more. When you divide, you're always going to end up with something that's linear, since we subtract our exponents to get the degree of the quotient. Our quotient is always going to be linear, so it's going to be some mx plus b and then a remainder. Since our quotient is going to be linear, our remainder is going to look something like just, 1 over x plus 5. That might be what a remainder looks like. And we saw with our horizontal asymptotes discussion that as x approaches positive infinity, a fraction like this is going to get smaller and smaller and smaller until it's practically 0. So we are going to drop our remainder. Because as x approaches infinity, that remainder is going to be approaching 0. So we're just going to drop it. And what we had before the remainder, this is going to be our oblique asymptote. Just don't forget to put y equals in front of it. So let's find our oblique asymptote. Now, the question's all going to be mixed up. It's not going to say find the oblique asymptote. So what we're looking for is the degree of the numerator 1 larger than the degree of the denominator? It is. So we can find our oblique asymptote by dividing. Excuse me. Notice that our divisors of the form x minus 2. So we could actually use synthetic division here to divide. I'm writing all the wrong numbers. Okay. We know that last number is our remainder. Well, we're just dropping the remainder. And this right here is going to be our oblique asymptote. We just got to write it correctly. Oblique asymptote at y equals, and we know that our quotient is linear. So that's going to be 1x to the first plus 5. Now, of course, you don't have to put the 1 in front of the x. I'm just trying to emphasize where I'm putting the numbers. Questions on identifying oblique asymptotes? Well, all right, let's put it all together in one giant problem and graph a rational function. So here's kind of our general steps. So I've got some rational function. The first thing we want to do is simplify the rational function and identify any holes. The way that we accomplish that is by factoring the numerator and the denominator. So I don't know, if you feel like you need to have that as your first step, step 0, then maybe you need to add that in. So that's how we accomplish step 1. Then we're going to find all of the asymptotes using the 3 types of asymptotes that we have. It's important that when identifying asymptotes that you're using the simplified version of the rational function. Then we're going to find x and y intercepts. We do that a lot when we graph because they're points that are easy to find. Again, you got to use the simplified version of the rational function when finding those intercepts. Then we're going to draw the intercepts and asymptotes. And then we're going to need to find additional points on the graph, particularly near the asymptote. So we're just going to make an XY chart Be sure when finding these points, though, that you use the original rational function and not the simplified version. We're going to plot the additional points. We will draw in our intercepts, asymptotes, any additional points, and then use a smooth curve to connect the dots. Let us graph the function g of x equals 2x squared minus 7x plus 6 over x squared minus 3x minus 4. We will identify any holes, asymptotes, x-intercepts, and y-intercepts. We'll also state the domain in interval notation. I would actually start with the domain. So much of this we use the simplified version for, but domain you use the original function for. So I would do it first before I simplified it, just so I didn't accidentally use the wrong one at the end. So to find our domain, set our denominator equal to 0, solve and exclude. We get that x can't be 4 or negative 1. Our domain is equal to negative infinity to negative 1, negative 1 to 4, 4 to infinity. Questions on identifying the domain? All right, moving on to holes and asymptotes. We want to factor our function and see if it can be simplified at all. So our numerator factors into 2x minus 3 times x minus 2, and we already did the denominator. X minus 4 times x plus 1. So are there any holes?
No.
No holes. No common factor, so that means we have no holes. And now we want to move on to our asymptotes. I usually do them in that order: vertical, horizontal, oblique. Doesn't really matter though. So vertical asymptotes, they exist at the zeros of our denominator. Oh, where will our vertical asymptotes be?
Four and negative 1.
Now, careful with your notation though. All right, we need x equals 4 and x equals negative 1 when we write that in. Next is horizontal asymptote. This is where we compare the degree of the numerator to the degree of the denominator. I personally don't like to look at a factored form to do this one. So ours didn't simplify, so I can just go back to the original. If it had simplified, I would have multiplied out anything that was left so that I could see better. I think it's easier for horizontal because this is where we're comparing the degree of the numerator with the degree of the denominator. In this example, they're the same. So what does that mean for our horizontal asymptote when our degrees are the same?
It means is it leading coefficient?
We're going to have a horizontal asymptote at the ratio of our leading coefficients. 2 over 1.
Yes.
So horizontal asymptote at y equals 2. Lastly is our oblique asymptote. This only exists when the degree of our numerator is exactly 1 larger than the degree of our denominator. Is that the case?
No, please.
No, it's not. So that means that here we don't have any. No horizontal asymptote. Or I'm sorry, no oblique asymptote. Also recall that an oblique and a horizontal can occur at the same time. Questions on our holes and asymptotes?
I think we're good.
Next up, we're looking for x-intercepts. To find any x-intercept ever in our lives, we let y be equal to 0 and solve for x. So we get 0 equals 2x squared minus 7x plus 6 over x squared minus 3x minus 4. We've got a rational equation to solve, but we have a special kind of rational equation, a proportion, because I can rewrite that as 0 over 1. 1 fraction equal to 1 fraction is a proportion, and I'm always happy to see a proportion because that means we can do what?
Cross multiply.
Cross multiply.
Cross multiply. So 0 times our denominator is just going to be 0, and then 1 times our numerator is just going to be our numerator. And now we want to solve. Well, I already factored this, so I'm not going to do the work again.
Wait, wouldn't that be dividing by 0 though?
No, because when you cross multiply, they're equal to each other, not divided by each other. Right, if A over B equals C over D, then AD equals BC. Not dividing. All right, so I'm just going to steal the work I already did from over there and not think again. And then we'll set each of these factors equal to 0, solve, and then we'll have our intercepts. So we get 3 halves and 2, but we need to be sure to write our x-intercepts as ordered pairs. And there we go. Questions, anybody on our x-intercepts? On to our y-intercept. To find any y-intercept ever in our life, we let x be equal to 0 and solve for y. So y equals, and it doesn't matter if you use the factored form or the multiplied out form. I typically like to use the multiplied out form here. And the reason I like it is because I can do it easily without a calculator, because all these zeros, any term with an x ends up disappearing, and you're just left with the ratio of the constants. So y equals 6 over negative 4, which is negative 3 halves. We get the ordered pair 0, negative 3 halves. At this point, we want to draw in everything that we have. which honestly isn't very much. I've got 3 points, 1.5, 0, 2, 0, and 0, -1.5. That's it. That's all I have for points. And then I've got a couple asymptotes. Verticals at x equals 4 and x equals -1. And you'll notice I'm drawing them in a dashed line because technically they're not part of the graph. They're just guidelines for us. And then we have a horizontal asymptote at y equals 2. I'm going to try to zoom out to see if I can make it so it's not so big. Oh, that's the opposite of what I should have done. Okay, so that's all the information I have. It's not much for our graph. So now we got to get a bunch of extra points. Our vertical asymptotes have kind of cut up our plane into 3 regions, right? We have the left of our first vertical asymptote. We have in between our 2 vertical asymptotes, and then we have to the right of our second vertical asymptote. Those are like our 3 regions. So what we're going to do is we just need to get some extra points in each of these 3 regions, particularly near the vertical asymptotes. So we're going to make ourselves an XY chart to get these additional points. So in that first region to the left of our first vertical asymptote, I'm going to pick the numbers -8, -4, and -2 because I need to get close to that vertical asymptote. Then in between, well, in between we have 3 points, and we know that these 3 points have to connect. And I also know that the ends of my graph have to tend towards the asymptote. This one is already so darn close that I am sure that it's just going to go this way. If you really wanted to do a -1/2 x value, you certainly could do that. Now, the right portion of this, I'm not sure. It could do like a swivel and then go up like a cubic function, or it could curve down and give us kind of a parabolic shape here in the middle. I'm not sure which, so I'm definitely going to choose 3 as one of my x values. And then I want that third region, that region to the right of our second vertical asymptote. So I'll go just on the other side, x equals 5, and then a little further out at 8. Yes, this is tedious that you have to put all of these into your calculator to get some ordered pairs. When you get to calculus, you're going to learn a much slicker technique for graphing. However, I think that what we learn in here algebraically about asymptotes is easier than what you learn about asymptotes in calculus. So I definitely think that knowing both techniques is important. I always have my calc students check their asymptote work with what they did in college algebra. All right, so I'm just going to pop these in my calculator. I did it ahead of time, so I already have them. And we'll plot our points. -8, 2.3. -4, 2.8. And then -2, 4.7. And then I usually like to connect the dots after I get a region done. I know these 3 points have to connect. And I also know that the ends of my asymptote have to tend, the ends of my graph have to tend towards my asymptotes. So this end has to continue and get closer and closer to our horizontal asymptote. And this end is going to continue and get closer and closer to our vertical asymptote. Questions on that region at all?
What did you multiply x by to get y again?
Oh, I had to shove it in this whole gross original function.
Oh, okay. All right.
Yeah,
Thank you.
that's why I did it ahead of time, so we didn't have to spend forever popping that in our calculator. Make sure you have parentheses around that numerator and denominator when you plug it in. Anybody else? Questions? All right, so this middle region, that's going to be this -3 or -0.8. So right here, so that means, right, these have to connect, and now I can be sure that as it tends towards the asymptote, it's got to be going down. So there's our middle region. Questions on the middle region? All right, last one. We have the point 5, 3.5. And the point 8, 2.2. Now, these 2 points have to connect. And the ends of our graph have to tend towards the asymptote. So this one on the left is going to tend towards the asymptote it's closest to. This vertical, and the one on the right tends towards the asymptote it's closest to. So there we are. Here's our graph in red. The green, again, are our asymptotes, not really part of the graph, just guidelines for it. That's why we draw them in with a dashed line. It's also why I used a different color for it. Questions at all? All right, let's try another one. Let's graph the function h of x equals x to the third minus x over x squared minus 2x minus 3. We'll identify any holes, asymptotes, intercepts. We'll also state the domain in interval notation. Well, just like the last example, I'd totally do the domain first. To find our domain, we're going to set the denominator equal to 0, solve and exclude. Factors nicely. And it will. I'm not trying to trip you up here, you know, we're not going to make the factoring super gross. We won't have to check possible rational zeros. So x can't be equal to 3 or -1. But we want everything else. Our domain is going to be -∞ to -1, -1 to 3, 3 to infinity. Questions on the domain? Next up, we're looking for holes and asymptotes. To identify holes, we need to factor our function. So we'll do that first. In the numerator, look, we got 2 things going on. We got a GCF of x that we can factor out, but then we're left with the difference of two squares. So this is really x times x plus 1 times x minus 1. And the denominator, we already factored when we did the domain, so I'm just going to steal that work. Can this be simplified? Sure can.
Yes, it can.
Okay, we got a common factor there. So this is going to simplify to be h of x equals x over x minus 1 over x minus 3. What does that common factor tell us? What do we have?
There's a whole at -1.
You got it, but again, watch that notation. We're going to have a whole at x equals -1. That's the 0 of our common factor. And now we want to do all of our asymptotes. Remember that for all of our asymptotes, we're using this simplified version for it. So starting with our vertical asymptote, are we going to have any?
X equals 3.
At x equals 3, as long as you still have a denominator after you have simplified, you're going to have a vertical asymptote, and it's going to be at the 0 of that simplified denominator. Horizontal asymptote, that's where you're comparing the degree of the numerator with the degree of the denominator. I mentioned before, I prefer the multiplied out version to do this. So personally, I would take a second and I would just multiply this out. And then compare the degree of the numerator with the degree of the denominator. We notice that the degree of the numerator is larger. What does that mean regarding our horizontal asymptote? That the degree of the numerator is larger.
No whole.
That means that there is
No
none.
horizontal. Sorry, no horizontal.
You got it. And then the last one is our our oblique asymptote. That exists when the degree of our numerator is exactly 1 larger than the degree of the denominator. Is that the case?
Yes, yes.
Yes, it is. So we need to divide, and whatever our remainder is, that will be our oblique asymptote. This one's eligible for synthetic division. So dividing here, taking 3 into 1, -1, 0. We throw out our remainder. Oh, I did this wrong. Oh, no, I didn't. I'm good. Oh, what is our oblique asymptote?
X plus 2.
Yes, but watch that notation. We got to make sure that we write oblique asymptote at y equals x plus 2.
I have question.
Yes.
For oblique notation, you are taking dominant and which one are taking for synthetic division?
Oh, well, so the only way we can do division is this one's underneath and this one's on the outside. Our numerator is always
whole.
our dividend and our denominator is always our divisor.
After whole, after you take whole out.
Okay, and then I did the vertical asymptote.
Okay.
That occurs at the 0 of our simplified denominator.
Okay.
Anybody else? All right, intercepts are next. Where am I gonna put this? All right, I'm gonna do, yeah, I can fit it right here. X-intercept. For any x-intercept ever in our life, we let y be equal to 0 and then solve for x. Oh, we got this proportion again. We can cross multiply. 0 times our denominator is 0, and 1 times our numerator is our numerator. So this gives us 0 equals x to the third minus x. To solve this equation, we want to get it in factored form, but remember, we already factored. Oh, shame on me. Look at me. What did I do wrong?
You didn't use the simplified.
I didn't use the simplified form. Let me show you what would have happened. I'm just going to carry out what I did wrong. All right, so I'm going to use the factored form here that we already came up with. And we're going to get 0, -1, +1. So I'm going to get these 3 x-intercepts. But look at this. We said over here that there's a hole at x equals -1, which means open circle, which means there's not a point there. And then I'm contradicting myself over here by saying that there's an x-intercept at -1, 0. So that right there is why you have to use the simplified version, because you can't have a hole and a point at the same x value. Now, I guess you could use the original version and then eliminate anything that you previously stated as the whole, but I think that's more risky than just using the simplified version. All right, 0 equals x squared minus x over x minus 3. But we will still be cross multiplying. 0 times our denominator is 0, and 1 times our numerator is our numerator. We get 0 equals x squared minus x. Factoring this, we're going to get x and x minus 1. We get x to be 0 and 1, and we'll write that as ordered pairs. 0, 0, 1, 0. Those are our two x-intercepts. Lastly, we want our y-intercept. All right, I'll put it down here. Again, using the simplified version, we're going to let x be equal to 0 and solve for y. And I prefer the multiplied out version, but you can use either. This gives us y equals 0 over -3, which is 0. We get a y-intercept. You could have skipped the work on finding the y-intercept, because if there's an x-intercept of 0, 0, there's automatically going to be a y-intercept of 0, 0 as well. All right, let's get everything we know on our paper. So I only have 2 points, 0, 0, and 1, 0. And then we have 2 asymptotes of vertical at x equals 3. And then we have an oblique asymptote at y equals x plus 2. You may be thinking to yourself, well, Allison, how am I supposed to graph that asymptote? The exact same way you would if you were graphing a line, right? We're going to start with a y-intercept of 0, 2, and then we have a slope of positive 1. So we get this. I'm not going to do it in the highlighter because it's going to be so super wide. It's going to be hard to see. So there we go. Questions on anything I did so far?
For oblique, how we draw the oblique?
Say that again.
For oblique, how we draw the asymptote? Oblique.
The second asymptote, so it was
Yeah.
y equals x plus 2. So I started with my y-intercept as 0, 2. And then we have a slope of 1. So we're up 1 over 1, up 1 over 1, up 1 over 1. And then we just fill it in. I just didn't want to really write points. I didn't want it to be confused with the actual points of the graph.
Okay, thank you.
No problem. Now to finish it up, we just need to get some extra points. We know that these two connect. And typically when you have one vertical and one oblique asymptote like this, almost every time, your graph's like opposite. So either there or there, or it would be like here and here. But we want to get, a better idea, not just draw it in all guessing. So I'm going to grab a few more numbers. I'm going to go 1, 2.
1 and negative
So maybe
1.
like -3. I'm going to go a little further out than that. So maybe like -3, -6, and +2 for this middle part. -6, -3, and +2. And then I'll do on the other side of that vertical asymptote, so like 4, and then maybe 6 and 8. And we plug it into the very original problem, not the simplified version, the very original version. And for the sake of time, I've already done that. I mean, -4.7, -2, -2, 12, 10, and 11.2. All right, so let's plot them. So there's my first region there. And I'm going to connect my dots, and the ends have to tend towards the asymptotes. So there's our first part. Any questions on that? And then we'll plot our other 3 points. I'm kind of curious what's going on at like, what is that? 5. I think I'm going to put another point in. I want to do 5, x equals 5. Because I'm not quite sure how that dips down and connects. So if I do 5, I get 10. All right. Well, at least that gives me a little bit better idea. I'm going to connect the points, and our ends have to tend towards the asymptotes. And there we go. There is the graph of our rational function. Questions, anybody? All right, well, that ends our section on rational functions. All right, it's Wednesday, so I don't see you till Monday. On Monday, we're gonna do rational polynomials, and I think variation maybe is next after that. They're both pretty short sections. We'll definitely get them both done in the same day. And then that's the end of the material on the next exam. So not next week, but the week after that, we'll be ready for our Unit 3 exam. Anybody? Any questions about anything?
Okay, so the week after this coming one is the exam.
Like, probably like 2 weeks, like 12 days from now, I'm thinking. It's probably on the, hell, I'm sure it's on the calendar. We're on schedule.
Okay,
It's like 12 days from now. So double check the revised calendar that I sent out. Anybody else?
is there any printout paper from this section that we should do?
Well, the take-home quizzes that are posted under the take-home module in D2L, I think it's I think it's what we did today and what we're going to do on Monday in one quiz. I think. So check it out though. Anybody else? All right, have a great week. See you
Okay.
on Monday.
Thank you.
If you want to
Thank
stick
you.
around, I'm doing office hours for the next half hour.
Okay,
Thank
one
you.
question though.